So, we've been investigating the consequences of a scale factor that is proportional to time, and given that assumption, we've worked out how old the universe would be. However, that's actually not a realistic assumption. That would only work if there were no forces. But in fact, the universe is full of things which have mass, and mass means there's gravity, and gravity sucks. It's a force that pulls things towards each other always. So in fact, what you'd expect is as things moved apart, gravity will try and pull them back together again. So the expansion rate will actually slow down.
So let's try one here, okay? So if we have this model is a model where there's a lot of gravity, it's slowing down, but there's not so much gravity that it slows down completely. It just keeps on getting bigger and bigger over time.
So here's a simulation of what this might look like. So it's expanding at a fast rate to begin with, but as time goes on, the gravity is pulling things back and slows the whole thing down. This is actually analogous to throwing something up in the air. If you throw a ball up in the air, gravity is pulling it down, but the higher it gets, the weaker gravity is. And so if you throw something fast enough, it can actually keep on going forever. The gravity is always slowing it down, but it never actually stops. It just gets slower and slower and slower. It's reached escape velocity.
Right. So this is what you need if you're going to have a rocket that's going to travel to the outer solar system, effectively.
So you can see things are ground to a halt, slowing down. It never stops, but slows down.
Okay, so that's one idea. What about one where there's lots of gravity? Gravity that's so strong that the universe actually does completely stop and start going in reverse.
So the scale factor goes up and comes back down again. And here's a simulation of that. So the universe expands fast, gets larger and larger, things drift apart. So this is where we would be in the universe today, the expanding phase.
Yep.
But if there was enough mass, eventually, it's like throwing a ball up at too slow a speed to have escape velocity. Eventually the ball comes up and then comes back down again.
That tends to be how the balls that I throw up end up.
Yes, that's telling you that the gravity overcame the force of the throw. So in some sense, the ratio of how fast space is expanding. And eventually everything comes crashing back together again in what you'd call maybe the big crunch, being the opposite of the big bang.
Or the Gnab-Gib, as I like to call it, the Big Bang backwards.
So this was the big debate in the mid-1990s. Which was it going to be? We knew space was expanding. We knew there was gravity, which was going to slow things down. The big question was, how much is it going to slow things down? Is it only going to slow things down a little bit, like the blue line here? So we'll keep on expanding, but slow down, but never stop. Or is it going to be a much more violent universe where it expands, we're still here, then turns around and comes back down together again? And that's the question you decided to investigate when you came here to the ANU back in 1996.
Yeah, so when we arrived, actually 1995.
1995, all right.
A year earlier, there was this opportunity to go out and measure the future and past of the universe.